In this class, we're going to take a look at the graphs of quadratic functions. So as a reminder, a quadratic function is made from a quadratic expression. So quadratic function f of x equals basically a quadratic expression, which in general terms is ax squared plus bx plus c, where a, b and c are some numbers, and the b and the c are allowed to be zero. In other words, that's allowed to disappear, and you've still got a quadratic expression, and therefore a quadratic function. So every type of function makes a type of graph. So for example, if you've already seen linear functions, so you could write a linear function as f of x equals ax plus b, but a more common form is y equals either ax plus b, or even more, I guess, common would be y equals mx plus c. And that is basically the equation of a straight line. So this type of linear function makes a straight line graph. So if we come to plot the points for this type of function on an xy axis, it's going to look basically like that. So it's the same when we move up to the next level, which is a quadratic function. These guys make a certain type of graph, and the type of graph that they make is called a parabola. So it's basically a U-shaped graph. And in general, the parabola is going to look something like this. So on an xy axis, it's going to look something like this. So they're symmetrical, they're not like lopsided, they should be symmetrical around a line of symmetry down the middle. They can be located anywhere, so I put this one here, it could be over here, it could be over here. They also go upside down, like inverted, to be an upside down U-shape, upside down parabola, and we'll talk more about those later. But the purpose of this class really is just to think about some of the general ideas and the key points that we need to think about for this type of graph. For a straight line graph, the things that we're normally interested in are the steepness of the graph, so like how steep the angle is, and then we're interested in, for example, the y-intercept, sometimes the x-intercept. Those are the things that kind of define that type of function's graph. With parabolas, the things that we're interested in are this point here, which we call the turning point, these points here, which we call the roots, and then this point here, which we call the y-intercept, just the same as the y-intercept on a straight line graph. So the whole topic around quadratic function graphs really centers around working with these key points. Finding those key points, working with them, recognizing how they relate to each other, and that sort of thing. We're not going to get into the technical details of any of the techniques for these in this class. We're just kind of setting the scene for where you might be going with this topic. So one of the first things to know is that if you've got a positive x squared term, so for example, if that was just x squared or 2x squared or 3x squared, so some positive number of x squared, so when you've got a positive x squared term, you get a U-shaped graph going that way, and we call this a minimum turning point, because the turning point where the graph changes direction is at the bottom, okay? So we call that a minimum turning point, so I'll just abbreviate that as TP for turning point. If you've got a negative x squared term, unsurprisingly, that flips the graph the other way around, and then you get a maximum turning point. Most of the parabolas you'll work with are probably going to be minimum turning points, but be aware of the maximum turning point, and it's all dictated by that x squared term. So just to put some labels back actually on this guy, so this here was the turning point. In the case of this one here, it's a minimum turning point. This guy here was the y-intercept. And then these guys here are called the roots. Okay, so there are a few variations of that as well. So let me just show you some examples over here. Parabolas can be located anywhere, so that means that you don't necessarily have any roots. So for example, if you're a parabola just floating in space like that, then the roots by definition are where the parabola cuts over the x-axis, but this guy never intersects the x-axis. So it's still got a turning point, which is this point here. It's still got a y-intercept, but it doesn't have any roots. So you'll see that fairly often actually, parabolas that don't have any roots. Similarly, you could have a parabola which, again, is a variation on this one, which maybe comes down Let me put this one over here. So it comes down like this, just touches the x-axis and goes back up. So in that scenario, it's only got one root. So it's just touching the x-axis at one single point rather than cutting it at 2 points like this. And that guy there is the turning point and also one of the roots. So you've got a few variations. Once you get into the mechanics of this topic, once you start working out these points and playing around with them and experimenting with the different techniques, then you'll start to see how all of these things sort of come together. So I think that's probably all we need to say about these key points on a function graph. Just to maybe leave you with a concrete example, just really to try and highlight what the graph of a function even is. I mean, hopefully you already kind of know a little bit about how to turn function sort of equations into their graphs, but essentially, if you take a function, let's say we've got f of x equals x squared plus 2x plus 2, something like that. Essentially what a graph is just a pattern of points. It's a bunch of points. Every point on the graph is defined by the equation. So what you can actually do is just generate sort of a table of values where you put your x values here and you put your f of x values here, and you just start to work up a few points. So let's say that we took just keep this really simple, minus 1, 0, 1, and 2, and just quickly work out the points that we get. So just putting those numbers into the function. So starting with 0, which is quite easy, 0, 0, 2, so we would get an output of 2. Looking at the 1, we would get 1, 2, and 2, which is totals up to 5. And then for the 2, we would get 4, 4, which is 8, plus 2 is 10. For the minus 1, we get 1, because it's minus 1 squared, so it's 1, minus 2 plus 2, the minus 2 and the plus 2 cancel, and we just get 1. So what these are that we've got here in the table are coordinates. These are pairs. These come in pairs. So these are coordinates of points on our graph. So whenever you're like drawing the graph of any function, what you're really doing is effectively plotting all the points or plotting enough points whereby you can start to get a feel for the shape of the graph and then just filling in the graph from there. So this will just be a very rough sketch. I might need more points to get a more accurate sketch, but the important thing is here, our expectation is that this should come out to be a parabola. And the reason we know it's a parabola is because we've got an x squared term. In other words, it's a quadratic function. Quadratic functions always make parabolic graphs. So let's check it out and see what happens. So minus 1, 1, that's minus 1 here, and then 1 up, so that would be like somewhere there. 0, 2, so 0, and then up to 2 would be somewhere there. 1 along is corresponding to 5. 2 along is corresponding to 10, which would be up there. So it's a very rough sketch, this. I didn't quite put in probably enough points to see the whole curve, but that's fine. We can see there clearly that this thing is curving through these points. Where it goes after that, I'm not quite sure. I would need to do more work, but it's probably going to carry on. It might cut through, probably does look like it cuts through there, and then it maybe goes up something like that. But I just wanted to put that example in just to concretize it a little and just to explain to you why you get a parabola graph or any kind of graph from a particular equation. You're never really going to have to do that because there's other methods, and that is really what the whole quadratic topic is about, exploring other methods to get from there to there or to go from there to there. It's a connection between the algebra and the kind of geometry that this topic is about, and it's also what makes this topic quite challenging sometimes. It's quite a nice topic, it's quite rewarding in the sense that you're moving up from linear functions, which is where you usually start with functions, up to quadratic. So you're kind of moving towards calculus at this point, which is kind of a stepping stone on your mathematical journey, I guess. So that's probably enough of an overview on this class. If you're comfortable with that stuff, then maybe start to move into learning some of the techniques.